This lecture series was founded by Dr. Abhay Ashtekar in 1995, soon after he arrived at Penn State as director of a new research center that subsequently evolved into the Institute for Gravitation and the Cosmos. And the series owes its success to the tireless efforts and meticulous planning by Barbara Kennedy, who presided over the series during its first 25 years, making it one of the most successful science outreach programs in central Pennsylvania. And so today, Professor Ashtekar, who is the founder and now benefactor of this lecture series, is with us here today. I'd like to ask for a round of applause just for the work that he's done for the series. And I'm going to hand him the mic because he'd like to say a few words about the origins of this lecture series and how he's seen it grow since then.
Okay. So we just heard this series started about 26 years ago. And the very first lectures were actually given by a postdoc. The entire series of 6 lectures were given by Robin Tully, who is a postdoc. You can see up here. And he really was extremely successful because he would be in Wegmans and he would be in the corner room eating his lunch, and people would come and ask him questions, and he couldn't finish his lunch, and so on. So we were very, very, very impressed by that, and that's why the decision was made by then Dean Joffrey to make this an annual event and continue. And now the format has changed a little bit. We got more senior people, many times people from both sides. We have had last year Nobel laureates come and give us these talks and so on. But Robin is shown here. He went on to an unusual career for a cosmologist. His lectures were on cosmology. And he became the director of research and development for racing engines for both cars and motorcycles. And he also won he himself actually rode motorcycles and won several championships. So it's very, very unusual for something like this. So that's how it all began. But then for about 25 years, this has gone on to very different topics. We have had topics like on becoming human, our planet Earth, also Einstein's legacy, sort of asking about big questions, and also questions that touch our life, such as this lecture series, which is predicting the future. Now, during these 25 years, we have had continuous support from the Eberly College of Science, the Office of Communications. Now that is headed by Joel, an outreach office up here. And then also the 4 deans who have served the Eberly College since then. And as already was mentioned, that this series really was sort of, its success really goes to Barbara Kennedy, who presided over this series for 25 years and handled particularly the question and answer session and so on with great professional skills. And so I just want to end this by thanking Barbara. Barbara, where are you? Yes. And finally, it's really wonderful for me I'm really proud to belong to this community, State College community, where in spite of bad weather and so on, people come here year after year to listen to the fundamental breakthroughs in science and how they will eventually affect our life. Thank you.
Thank you so much, Dr. Ashtekar. As he alluded, there is a theme to this year's series, and this year, the Ashtekar Frontiers of Science lectures are entitled Predicting the Future, Improving Lives and Communities Through Modeling. So this series explores how scientists, policymakers, and communities increasingly are using data science to plan for the future in our ever-changing world. From disease forecasting to identifying potentially habitable worlds outside our solar system, the series will provide examples of how life scientists and physical scientists alike are using statistical and mechanistic modeling to improve lives and society. And so today's featured speaker is Dr. Murali Haran. He's professor and head of the Department of Statistics here at Penn State University. He has a PhD in statistics from the University of Minnesota and a bachelor's in science in computer science with many minors in statistics, mathematics, and film studies from Carnegie Mellon University. His research interests include Monte Carlo algorithms, spatial models, statistical analysis of complex computer models, and interdisciplinary research in climate science and infectious disease modeling. Haran is a fellow of the American Statistical Association and received the 2015 Young Researcher Award from the International Environmetrics Society, an award meant to recognize and honor outstanding contributions to the field of environmetrics. So today, Professor Haran will enlighten us on statistics and the future of the Antarctic ice sheet, with a focus on the role that statistics plays in climate science and how scientists make projections about future climate using statistics. So Professor Haran, thank you so much for being here today. We really look forward to learning about this interesting topic from you.
Thanks, Jessica. Everyone can hear me clearly? Great. So first order of business is getting my PDF up. Okay, great. Thank you all for coming. I know that there was some dicey weather predicted, less dicey in actuality than was predicted. And guess what? We're going to be talking about predictions today. And perhaps, really importantly, decision-making under uncertainty. So I received an email a couple of days ago saying that the weather was bad enough that there was a whole group of people who were planning on coming, but they decided that it was a little too dicey, and they decided they were not going to come, and I don't see them here. So they made their decisions in one way, and you made a decision another way. And we'll talk a little bit about how we all have to make decisions under uncertainty and some statistical insights into how you can think through it in sort of a careful, rational way. All right, so just a quick thing. So I'm the department head, and I'm the first speaker in this series, which is a lot about statistics and data science. So I feel like I should start with some general stuff about statistics. So first thing is there's this quote, a recent quote by Hal Varian, where he said, the chief economist at Google, where he said, statistics is a dream job of the next decade. About when I was a PhD student, I don't think it was considered the dream job. When I was a computer science major at Carnegie Mellon, and all my friends went off to make millions out in Silicon Valley. I was the weird one who went to do a PhD in statistics. But now there are lots of people who are doing PhDs in statistics and data science who may have even started off in computer science. There's just a shift in how people are viewing statistics. And here also, I'd like to point out, US News and World Report says it's the #1 business job and has a #2 ranking in best jobs overall, is to be a statistician. Quite a shift. And there's generally more statistician and data analyst jobs than there are qualified candidates. Okay, so this is just broadly speaking about statistics. But we're here to listen to talks about statistics and science. It's the Eberly College of Science. So it turns out that the #1 business job is also central to science. So I'm just going to list a few things. It's like somewhat my personal view of how statistics is central to science. I think most people who use statistics in science would agree with the gist of this. So few things that we do with statistics in science. One is discovery, so finding information and patterns in data, and our data are getting more and more complex and massive. So finding a gene out of thousands that might be related to a disease. Separating signal from noise. There's even a book some time ago called Fooled by Randomness. So you don't want to be fooled by randomness, and statisticians are really focused on trying to help scientists not be fooled by randomness. So did this medical treatment truly help patients, or did they get better by chance or some other reasons? Synthesis. This is a lot of what we do, especially I do with a lot of my collaborators, which is figure out ways to combine different kinds of data with scientific insights in a rigorous fashion. This is not easy to do, and statistical methods are pretty central to this. So for example, understanding ice sheets from satellite images of ice sheets and ice core data, and then mixing that in with the physics of ice sheets. How do you put that all together? Statistics gives you a way. And then finally, decision making. So you need probability to assess risk. You need to make a decision. Do I venture out this morning for a Frontiers of Science lecture? I've heard something about the forecast. How risky does it sound? And what is the potential gain I might get by actually going to this lecture, right? So things like that. But maybe a more serious decision-making problem is how high do you want to build levees in New Orleans? Okay, the other great thing about statistics, which if you're not in statistics you don't always see, is that it really combines all sorts of ideas from different ways from different disciplines. One thing that's really fun is that there's a lot of philosophy in statistics because really you're thinking, the philosophy of science, how should you weigh evidence? Sort of the fundamental nature of truth. What you see is not really what's happening, it's a version of it. How do you make connections to what's happening? Randomness. What is the meaning of randomness? Lots of interesting philosophical questions. There's computer science, which was my background before I got into statistics. So you can come up with lots of clever statistical methods, but if you cannot compute for those methods, especially with larger and complicated data sets, you're out of luck. So computer science is pretty central to modern statistics. Mathematics, so if you want to understand the properties of what you're doing, I have colleagues who spend their entire time proving theorems. So it's really a melding of a lot of these disciplines. And then the other very exciting thing for me, especially and for many of us, is multidisciplinarity. So it's building statistical models for research in an enormous number of disciplines. So I actually work on two, and I was very excited to see collaborators from each of those disciplines here. So my collaborators from climate science, Klaus Keller, collaborator from infectious disease, Kat Shea, and maybe some others here too. And also, if there are really hard science questions, I can always just point to them instead. So I was especially excited for that. So the best thing about being a statistician, this is a very well-known quote in statistics by John Tukey. The best thing about being a statistician is that you get to play in everyone's backyard. So if after a few years I suddenly decide that I want to get into neuroscience, I could do that. I won't be the world's expert in neuroscience that my collaborators might be. I'm certainly not the expert in climate and infectious disease that my collaborators are. But I get to pick out little bits and pieces of those fields. It's really fun. All right, so that was just a quick intro to statistics and the excitement of statistics in science. And then here's just a quick sort of promotion of the rest of the series. So we're talking about ice sheets today. There's predicting plant diversity on January 25th. On February 1st, there's animal movement and disease. February 8th, characterizing potentially habitable planets, so from astronomy. So Penn State is really strong in astrostatistics. And February 15th, disease outbreak control. Penn State is very strong in infectious disease as well. And then February 22nd, genetic mutations and childhood obesity, another one of our strengths. So lots of very exciting things to look forward to. All right, so let's cut to the main subject today. So what are ice sheets? So I always like to start any talk that I'm giving about ice sheets with giving a sense of just how enormous they are. All right, I just used the word enormous. So they're an enormous mass of glacial land ice, and they're supposed. The definition is if they're larger than 50,000 square kilometers, then they're an ice sheet. Okay, so there's two ice sheets, the Antarctic ice sheet and the Greenland ice sheet. And those two combine for over 99% of the freshwater ice in the world, which is quite an amazing thing. So here's a photo of the Greenland ice sheet. It's over 1.7 million square kilometers in area. The Antarctic ice sheet is way bigger than that. It's over 14 million square kilometers in area. And I'll give you a little bit more perspective on that in a few minutes, in a few seconds. All right, so ice sheets are enormous. They're pretty interesting. Why statistics and ice sheets? Well, if you want to understand the science of ice sheets, so how are they moving? How is a particular ice sheet moving? How is it evolving? How is it interacting with the ocean waters that's surrounding it? And lots of interesting features of the details of ice sheet physics. How do you understand that? And then if you want to make projections, how much of the ice sheet will melt in the next century? And then if you want to make decisions, how should we plan for ice sheet melting impacts, in particular sea level rise? And statistics has a great role to play in answering all of these questions. So it's worth pointing out that Penn State is one of the best places in the world for studying ice sheets. We have a number of great researchers here. And just pointing out a couple of the centers here, Penn State Ice and Climate, PS Ice, and CLIMA, which is the Center for Climate Risk Management. The director is seated right here, Klaus Keller. We're a university that's really quite good at this, at studying ice sheets. Okay, ice sheets and sea level rise. I love this picture. I used to, it just quickly tells you something that isn't obvious at all, is that this is the Antarctic ice sheet. This is the entire continental US. That is an amazingly huge thing. And think of how thick it is, around 2 kilometers thick. That is an enormous amount of ice. This is quite stunning how big it is. And so when there's that much ice, well, of course, that's a lot of water, frozen water. And if all of the Antarctic ice sheet were to melt, I'm not saying that's going to happen. I'm just to give you perspective on it. That's the equivalent of 58 meters sea level rise. That is just stunning, right? And the Greenland ice sheet, which is the smaller one, is the equivalent of 6 meters sea level rise. And then the other smaller guys, the glaciers and ice caps, are still the equivalent of 0.4 meters. That's quite a lot. All right, so I don't know if you can see this, but this is sort of this is the octopus photo that many of you have probably already seen. But this is a Miami parking lot on a sort of a regular-ish day, and there's an octopus. I don't have anything deeply scientific to say about it, but there's an octopus in a parking lot. That's interesting. But the interesting thing to note about this is that even if you have a modest contribution to sea level rise, this can have a major impact on humans, and actually we're seeing quite a lot of that already. So especially if you're in a low-lying area, places that are below sea level or close to, and areas that are prone to storm surges, this can be pretty dangerous. And here's another great picture. So no wake zone, which I'm told, I don't drive speedboats, but I'm told that usually you see them on lakes, and you're not supposed to splash people and drive too fast in that area. But it turns out that this is just a regular street in Fort Lauderdale, and this is sort of a certain kind of adaptation, I guess, is you put up a sign like this on a regular street. Okay, and this is another stunning photo. So a question here is, you might ask, where should we build? Where do we want to continue to build given some of these threats that we're facing? And then you look at a picture like this and you might say, how high should we build walls? How high should we have protection set up? So this is Hurricane Gustav in New Orleans, and sort of just menacing this policeman out here. So, and you can imagine that if there's a little bit of sea level rise and then there's a storm surge on top of this, that's really bad news, right? So how high do you build a wall? So here are certain questions that involve having to actually say something about the future. So there's a great quote. It's tough to make predictions, especially about the future. And I agree. That's a surprisingly deep comment. Okay. So here's the question. If you can't get the weather right in 5 days, how could you possibly make a prediction about the ice sheet in 50 years? Some of the people who didn't show up to the talk today may be asking a question like that. And because they didn't come to the talk, they'll never find out. And why I put this photograph up here is because I didn't make up this question. It wasn't sort of me asking myself this question. I was asked this question by a staffer of a congressman. Several years ago, I went with a group of scientists to talk about science policy and how it should be taken into account in policy in general. So maybe, to talk more to scientists when formulating policy. And if you've been to Capitol Hill, you know that lots of the work gets done by very polished, extraordinarily young people. And one of these very polished, extraordinarily young people, and very smart too, and very confident, asked me this question. Asked me this question. Sat back in the chair and said, "If you can't even do that, how could you possibly be doing any of this? How could you possibly make predictions in 50 years?" But this is actually a really excellent question, an outstanding question to ask. And so I'll tell you the answer that I gave him on the spot. As I talked to him about baseball. And so I'll confess, I'm much more of a football fan than I'm a baseball fan, but the baseball analogies are extremely effective, so I use them. So here's a question. If you have, so for those of you who don't know baseball, this is a person hitting a ball and then scoring runs, okay? So if you want to guess what this person, let's call him Joe, what he will score the next game, if you're trying to guess what he'll score the next game, is that a good idea for you to guess what he'll score the next game? Not unless you're a gambler, right? And sort of in the worst way, it's just you just want to go with something that's a gamble. However, it's not a terrible idea to try to guess Joe's batting average for next season, even though next season is a year off and tomorrow is tomorrow. So it's not a terrible idea to do this. All right, so why did I suddenly tell you this weird baseball example? Well, the analogy is that the next game individual performance is like weather, and the average for next season is like climate. There's just, when you're trying to say something about averages over an extended period of time, you can say things much more sensibly than you can about something that seems a lot simpler and much closer to now. Okay. And then the other thing that we also have when we're looking at climate is we have physics, which is great. That helps us do things that you couldn't do otherwise. Right? So you're not simply taking data and extrapolating, which if you've ever taken a stats course, that's the first thing you're told, don't go beyond the support of the data. That's a bad idea. If you have physics, you can do lots of interesting things. Okay, so here's a quote that many of you have heard, if you've heard talks about climate and stats, but if you haven't, it's a really succinct way to think through this. Climate is what you expect, weather is what you get. Okay? And in more technical terms, weather is a realization. Don't worry too much if you don't know what these words are, but just absorb the words for a second. So weather is a realization, climate is a distribution. So these are dice. Most people here have rolled dice at some point in their lives, right? If I pick two of these, if I just roll two dice, and then I looked at what the total of those rolls were, I would say, maybe your total was 6. So you got a 4 and a 2, so your total is 6, and you report 6. That's like weather. That's just what actually happened, okay? You roll the dice, you add the total of those two dice, that's like weather. But what's climate like? Climate is like the distribution. So that's something that's sort of the property of the dice. So if you had to actually look at this total of two dice, the rolls of two dice, would you think that one was, one is not probable at all. 2, would a total of 2, that was also a legitimate question to see if you're awake, but is a total of 2 more likely or a total of 7 more likely? 7, right? And you can see 2 can only happen if you get the 1 and the 1. 7 can happen in lots of ways. 6 and 1, 1 and 6, 5 and 2, 2 and 5, 4 and 3, 3 and 4. Right? So there's lots of ways that can happen. So if I look at these values that I've written down here, so I have values for these totals, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. These are all the possibilities for the sum of the two. 7 is the most probable, as we were just discussing. 2 not so probable. It's the least probable, and 2 is as probable as 12, which is why they have the same height. So what you see on the y-axis is the probabilities. So this is a distribution. So now you can think about a realization versus a distribution. If I roll these 2 dice, I look at the total, that's a realization. You know, I might get 5 now, I might get 7, I might even get 2, right? Not as likely, but I might get it. So that's like weather. And then if I do this over and over again, in the long run, I would get, if I plot sort of a histogram of this, just looked at the long-term averages, I would get something that would have way more 7s than other things. So what you want, the image you want to have is I roll this once, that's like weather. I roll these things lots of times, that's like climate. But really what climate is telling me is what kind of weather is more likely than other kinds of weather. That's one of the central ideas that I wanted to communicate to you this morning. Okay, so the result of a particular roll of dice is a realization, as I was saying. So weather is like seeing what happens when you roll the dice. So for example, the high temperature on January 17th, that's weather. That's like a roll of dice. But it comes from a distribution, right? And so climate describes what tends to happen in the long run. So it's a distribution of temperatures on January 17th, let's say, the same date, but over 1910 to 1940, right? Or, so that's in the past, or in the future, 2030 to 2060. And if there's climate change, then you think that this might be a little different from that, okay? But it's not that the weather is different on this day from that day, it's that the distribution of weather is different. So that is a key point of this talk. So how do you actually predict weather? I don't really want to spend too much time on this, also because I know very little about it. But at a sort of a superficial level here, quickly. So how do you predict weather on any particular day? You use numerical models, computer simulation of the atmosphere for the next few days, based on physics. Okay? So you take numerical models, and then you take data, which is lots of information over the last several days on temperature, humidity, wind, et cetera. And then you do this thing called data assimilation, which is you put those 2 pieces together in some sensible fashion. And there's been lots of time and effort invested in this because this is clearly useful. And you make a forecast. And that's actually how you heard that there was probably going to be some bad weather today. So you cannot make accurate forecasts beyond a few days because the errors in these things, for those of you who know these stories, the system is chaotic. The errors in these things just accumulate like crazy very quickly. A few days out, you're okay. A few days further out, not so much, right? Okay, so if you're talking about climate projection, it's quite different. So climate tells you probability distribution of weather events over an extended period of time. So by default, somehow, it ends up being about 30 years. That's not set in stone, but that's sort of the default. So for example, if you're trying to figure out the average low temperature on January 14th between 2050 and 2080. So that might be a climate projection. And what you do here is you use climate models which are based on physics, and you run these forward, and they're to give you roughly what you think you might get in terms of weather. And so what the climate model is giving you is something that looks like this. Okay? That's at least the mindset that you should have when you're thinking about climate projections. And then you still need to use data because you have a climate model. You want to sort of calibrate it. The word we use often is calibrate. We want the model to be tuned based on the data. So if it does pretty well, based on past information, we can fiddle with it. The scientists fiddle with these things until they get something that looks more like reality. Okay, so this is clearly still challenging, but you can actually project quite far into the future. And sea level rise, if you're interested in saying something about what might happen with future sea level rise, you want at the end of your analysis not to say something like, we think it's going to be 0.2 meters sea level rise in 2100. Instead, you want to say something, you want to provide a distribution. And I'll also explain why that distribution is useful for decision making. And we're starting that discussion here. Right? So this is something, you need to understand something about the cost. If you're making decisions, you need to know the cost of making, of outcomes, right? So the outcome here has to do with sea level rise. So if I put down water level, so these are different sea level rises in meters. For each of these things, this is from a particular paper. The details are not important, but I just want to give you a sense of how this might be done. This blue curve here, the curve above, is telling you how sea level rise, each sea level rise value is related to a cost. So I plotted also this line here, which says if it were sort of a linear relationship, or something that was kind of linearish, this one is highly nonlinear. So as you can see, as the sea level goes up, going from 2.5 to 3 is a much bigger cost than going from 1 to 1.5, right? So the costs are typically nonlinear in this fashion. So if you get a distribution like this, even if you get something that's a pretty low probability event, this is, by the way, please don't take this figure seriously. This is just to give you a sense of what a distribution might look like here. But if you have a low probability event way out here, you still have to pay attention to it because the low probability event might be extremely, extremely costly. So when you're budgeting for things and when you're making decisions in the long run, you need to really worry about, this is called the tail of a distribution, right? And my colleague here, Klaus, every talk he ever gives, he will talk about tails of distributions because he understands climate risk. And climate risk is largely focused on thinking quite a bit about the tails of distributions. So if you're doing a risk analysis for sea level rise, you would put these two pieces together, and you'd take this thing, the value out here that's low probability, so you take this high cost and you'd weight it less. And then you might weight the more probable thing by its cost. You'd weigh that more, but if you took the overall cost, that ends up being quite high if this probability is not negligible. Okay, so the tail of the distribution of the low probability events, they can be extremely costly, so it's pretty important to estimate them carefully. So how do we go about doing things like this? So this is just a review of what I just discussed, which is to make decisions, you need probability distributions associated with future sea level rise, and you need costs associated with each of these values. And it's important to understand the full probability distribution, not just averages. We want the full distribution. Okay, so I hope that that's good so far. So I'm hoping that I'm not speaking too fast. Okay. All right. Decision making under uncertainty. So I'm going to take an example from our own lives, I would say. I'm pretty sure you have the same experience as me. So let's start off with how high do we build levees on the coast? Instead of working with that example, which is really hard to understand right away, to think through right away, let's do something much simpler. Should we buy airline ticket insurance? Every time I buy a ticket on United now, it offers me airline ticket insurance, right? So it offers insurance. It says full ticket refund if you have to cancel due to a covered reason, and there's some fine print about what those covered reasons are, of course. So let's say your ticket costs $300 and the insurance is $30. Is it worth getting this insurance? Good answer. Good answer. In general, it's not worth getting these insurance things, right? Not these sorts. Okay. So I'm going to do a very quick calculation just to give you a sense. Let's say you get sick 1 week every year, okay? So that's approximately 0.02 probability that you're sick any given day. There's some assumptions there, but fine. We're just doing something simple. So any given day, there's a 0.02 probability that you're sick. And with insurance, you spend about $30 whether or not you get sick, right? You've tossed the $30, that's gone. Goodbye. Without insurance, but of course, if you pay insurance, you're not going to lose the $300. That's the nice thing about it, right? Without insurance, with probability 0.98, your loss is 0, right? Because you're not going to get sick most of the time, so you don't lose anything. With probability 0.02, your loss is 300 because there's that 0.02 probability that you get sick and then, oh no, you've lost $300. So if you wanted to make a decision based on expectations, you would just weight this. You'd say 0.98 times 0 plus 0.02 times 300, and that'll give you $6. And in the long run, no insurance means that you lose $6 on average, whereas with insurance, you lose $30 on average. And I'm very good with numbers. And this is losing $30 is not as good as losing 6. So don't get insurance, right? Based on this little example. So it's not a good idea to buy insurance for this case. But when we're talking about sea level rise, that's way more complicated. So if you're looking at insurance against sea level rise, let's say you want to decide how high you want to build a levee in New Orleans, instead of two possibilities, flight canceled versus not canceled, your trip canceled versus not being canceled, there are many different potential levels of sea level rise, right? And instead of just two possibilities for actions, instead of just buying the ticket or not buying the ticket, there's lots of possibilities. So you don't build anything, or build at a certain height, or build it higher. So the decision making is more complicated, but the principles are essentially the same. Okay, so that's the point I want to get across. So I've gotten across one point to you, hopefully, the difference between weather and climate, and sort of the statistical concept behind it, realization versus distribution. And here's another concept, which is probability distributions on outcomes and costs associated with those outcomes, and putting those pieces together to make decisions. So I'm hoping these things are clicking. Okay, so here's the halftime summary. It's not really halftime, so don't panic. But let's pretend it's halftime. Okay, so the climate it's a distribution versus weather, and then this idea that you can't predict weather beyond a few days, but it's reasonable to project the climate 50 years in the future. And to project climate, we need to combine physics with data. Okay, so statistical methods. We need statistical methods to do this, and for decision making under uncertainty, we need statistical methods. Okay. And so the second half, predictions. So the answer to the question, I will provide some idea of the answer to the question, how is statistics used to make projections about ice sheets? So I have to quickly acknowledge that this kind of work happens across several disciplines. So rather than read out all of this, let me just tell you that this first bullet here is about the ice sheet modeling. We have a world-class ice sheet model here, Dave Pollard. And this is mathematical the model and the computer code that simulates ice sheets. Okay, so that's kind of work that Dave does. And then this other group led by Klaus, which is understanding risk, decision making, climate, and also just climate science in general, but really targeted towards understanding risk. And then me and my students working on statistical methods for putting all these pieces together. Okay, so projections, as I said before, you cannot simply extrapolate based on data alone. So things are changing over time, and we let physics guide us. That's the central idea in the slide. So you need physics to guide us, and you still need data. And so what we will do is we will build models that combine physics plus account for lots of randomness and errors, and actually take the data into account when making any projections. Okay, so what's a model? I've been saying the word model a few times, and some of you know what I mean, but many of you may not. So a model is simply a reality. And so this is a kind of model that kids would like, many adults too, I guess. Miniature trains. So this is usually a simplified representation of reality. So what's a mathematical model versus a statistical model? A mathematical model is a representation of reality in the form of mathematical equations. So you describe how some real process behaves using physics and translate it into mathematics. So a statistical model is really, it's a mathematical model with some stuff on top of it, which is, it accounts for two very important features. So one is it accounts for randomness. You can't be sure of what happens. The other thing that it does is it accounts for the fact that the mathematical model is usually not a perfect representation. So I'm saying these things sort of quickly, but there's a lot of deep philosophy and thinking that goes into this, and sort of the philosophy of science. Very interesting things to think about. But from a very practical point of view, what this means is that a statistical model is a very nice, tries to provide a really realistic representation of reality. Okay, so here's a quick look at a model, at an ice sheet model. So this is a cartoon version of an ice sheet model, but it gives you a pretty nice idea of the kinds of things that one needs to worry about with ice sheets. So everything you see here that's white is ice, and then these arrows, just think of arrows as precipitation. So there's snow coming down here, and then as the snow keeps accumulating, it starts compacting, and at the bottom it starts hardening, and there's layer upon layer added. And then some of this will also begin to drift and slide down at different levels. And then there's basal sliding, so it'll slide on the bedrock here. And so how quickly it slides here, so there's a sliding coefficient that tells you how quickly it might slide. There's also something else that tells you how the ice sheet interacts. So this is the ice shelf, which hangs out over the ocean. How it interacts with the ocean water, which is, if it's warming especially, this stuff might melt, and then things might break off. So that's the process called calving, C-A-L-V-I-G. And this ice shelf, a piece might break off and then becomes an iceberg. And, all right. I did well the first 3 times, but okay. Okay, so you can see that there's lots of things. This is a very dynamic system. Things are happening. Things are moving around. And Richard Alley, famous scientist at Penn State, always talks about his analog is batter. And you know, the stuff moves, it hardens, and then it sort of moves around based on the physical characteristics of the floor, and so on. So there's lots of interesting physics that goes into this, and this gets translated into mathematics. So it gets translated into something that looks like this, and there's several. This is just a small glimpse, and I'm not going to walk you through this, but the idea is for you to see all of this gets translated into things that look like this and lots more of it. Okay. And what essentially happens is you take all of this, the physics is described in terms of mathematical equations, which then gets translated into computer code. Okay? And once you have the computer code actually mimics the behavior of the ice sheet. And so one way you can do science with all of this is you use computer experiments that are carried out with these models. And so you can fiddle around with different characteristics of this and see what it does to the ice sheet. So it's like a sandbox, right? Except with ice. And so you might see things about outside forcings, things that interact with other components of the atmosphere, and the effects of human activities and so on. So this is how you start. You build a model. And then where does statistics come into the picture? Well, there are several dials of this model. So for example, the slipperiness of the ocean floor, sensitivity to ocean temperatures, things like that, what I just described a few moments ago. If I dial up these things in different ways, and so change these knobs on this model, then I get different kinds of ice sheets. I get ice sheets that do different things. So for example, for these settings, maybe I'll get a model output of the ice sheet that looks like this in 2010. And then down here below, this is the satellite image of the same ice sheet. So if you compare these two things, you go, wow, that model's doing really quite well, right? And in case you're worried that I just replicated the same thing twice, they're not the same thing. So there are differences here. So you'll see that there's a little bit more ice in here, a little less ice here. It's not exactly the same thing. But the idea is that these models, depending on how you dial up, change the dials, will do different things. And now you can imagine that that tells you different things about the past of the ice sheet and the present of the ice sheet, and also the future. Okay? So this should help you understand that thinking about the dials of the model is really quite important. So, and just to give you another glimpse again from papers, from recent papers of ours, here's the observational data. So the white is the ice and the blue is not ice. So this is the actual data from satellite. And then these are 3 different dial settings. And if you look at these 3 different dial settings, you might go, well, this is no good, right? This is not that good. These 2, they're quite good. You might prefer one over the other. So there's consensus emerging here that one is preferred here. That's great. So the question is, what do you do with this? Remember, what we really want are probability distributions on things. We don't want to just say, this is what we think is going to happen, because if we say this is what is going to happen, we're going to be wrong because we don't know for sure. We want to say, these are the things that are more probable, these are things that are less probable. So we might take this kind of information and in a careful statistical fashion, figure out a probability distribution on these dial values. That's what we're going to do. So we don't want a single best dial value. We want to end up with a distribution for these values. So that is which values are more likely and which ones are less likely. And for this, and I'm going to give you a 30-second sketch of something that takes many years to learn. It's this notion of using Bayesian inference to do this. And the idea, high-level view of this is you start off with what's called a prior, which is a parameter distribution. It's a distribution on those dial values, which I also refer to as parameters. And you say, this is what all scientific knowledge so far and basic understanding of physics tells me these values might be. So this is before we see the data. And then we have a statistical model that tells us how those dial values are related to what we observe. And then we put those pieces together to get the posterior distribution, which says, this is now what we think about the parameter distribution, having seen all the data and putting down a model for all of the data. So that's my 30-second version of describing this very nice, very generally applicable way of doing statistical inference for problems like this. So a couple more things to note. So this, I'm hinting at some of the challenges. So I'm taking this kind of problem, which note that the kinds of data that we get are also, there's a lot of noise in these things, right? We have interesting issues with the satellite images and other kinds of data that we use. We need to account for all of those things carefully. In addition to all of that, these models, they turn out to take they can take quite a long time to run. So even on fast computers, it can take hours or days to run the model at even just a few settings. So if you want to just study the model, by just constantly running it at different values, that's not really feasible. It just takes too long. So there's nice statistical approaches that can help solve this. So there's some statistical cleverness that can help. So you can construct a statistical approximation called an emulator that replaces the original model. You learn a little bit about the model by running it a few times, and then you build this approximation, and then you can use this approximation to study the relationship between the dial values and what you observe from the model. Okay, so this is another little piece that our group has worked on for about the last decade on these kinds of methods. So what ends up happening after all of this hard work? And I'm just giving you a bit of a glimpse, and I'm not going through the details here again, just to give you a sense of what the end result might look like. We might get things that, these things that I've written out here are these parameters or the dials on the model. And what you're seeing here are the things that are in red and blue represent the values that are more likely and less likely. So the red, the very deep red is most likely, and as you get to the bluer values, that's less likely. So these are all probability distributions that we've learned by using all of the data, the models, as well as the statistical methods that we've developed. And so this gives you an idea of these dial settings. And if you understand the dial settings, then you understand also a little bit more about the underlying physics and what's happening with the ice sheets. And you can use that to then run the models forward and make projections under different scenarios. And that can give you an idea about sea level rise values. And again, these distributions, think of it as sort of distributions being put into that box, and then you run this black box model, and then you run it, and then you get output, which is also in the form of distributions. It doesn't literally happen like that, but that's a good image to have. Then I get a distribution for sea level rise. And remember the picture that I showed you way back when, which is this toy example here. So then we can get pictures that look kind of like this, and then I can put it together with pictures that look like this of costs, and that allows us to help with decision making. Okay, so I'm going to wrap this up here by telling you a few things that I've told you about. So after all of this hard work, are we sure that our projections are exactly right? Of course not. So that doesn't make this any less scientific. In fact, it's central to science. So ice sheets and the physical world in general are extraordinarily complex, and we cannot know the future exactly. And these projections are made under many assumptions about the model, the data, and future scenarios. Okay. However, uncertainty is not the same as not knowing. So sometimes people say uncertain, it sounds like, oh, I'm uncertain, I don't really know anything. That's not true. Remember that uncertainty is described during these probability distributions. It tells you some things are more likely than others. You can rule some things out, but some things you cannot rule out, and some things you think are very likely. So there's information there. And in particular, uncertainty is not a reason for inaction. So if you're making decisions, you're not sure if you're going to get sick the day that you're flying out of state college, but you still made a decision about that insurance policy, right? And we can make sensible decisions even if we are uncertain. That's an important point to make here. And of course, describing uncertainties carefully is central to the scientific enterprise. So statistics is clearly central to science. And statistical thinking more broadly is central to science. And you'll see a lot of that in the talks that come up in the next few weeks. Okay, and the last slide, I'd just like to thank several people who gave me useful comments and feedback on this talk. Questions?
Right, thank you so much, Professor Haran, for that awesome talk. I think some of the methods that the statistical concept that you mentioned will be really helpful for understanding some of the future lectures in the series. So I think this was a great way to kick it off. So we have our Science Lion Pride volunteers in the audience. So please hold up your index card with a question if you have a question, and they'll bring them over to me. There's some cards being held up, so they will be brought down to me so I can ask them of Dr. Haran. But first, I wanted to pose a question while we're waiting for things to trickle in. You mentioned how frequently statisticians collaborate with people from other fields, many other disciplines. Can you give us a little sense of how statisticians can successfully approach these kind of collaborations when you might not already have a background in the discipline that your collaborators are coming from?
Okay, thanks. Well, I can tell you the climate stuff, and it's really great that Klaus is here. So Klaus Keller is a professor in geosciences. Essentially sent me an email when I was a new faculty member at Penn State and said, I work on climate. I hear you work on statistical computing and Monte Carlo methods and Bayesian inference. Maybe we could chat. And I said, sure. And turns out he's brilliant, and he has lots of fantastic problems. And we started working together. And I didn't necessarily know where we were headed when we started working on these projects. But the really cool thing about a lot of these problems is that essentially, at some level, he showed up with, here are these are the kinds of data we have. this is kind of model we have that we run it at different settings. Let's find a way to put it together to figure out these kinds of probability distributions that I showed you at the end. So great. Now, how do we do it? And then I think we spent about 2 to 3 years getting on the same page. These things take a long time. I'm not trained in atmospheric science at all, and I still don't know that much, but everything that I do is with him or other collaborators that I have. So, and he doesn't have a PhD in statistics, so everything he does, the statistical stuff I will lead. And so it's this great thing where we get to be experts in our own field, dabble in the other field, and then do really cool and interesting science. And this is also true with several of the other collaborators that I have. As I may have mentioned, I work with infectious disease researchers. Again, somebody said, we've got these problems, I think you might be able to help us. Took a few years to get on the same page, and now we have all of these. Also, I should mention, there are PhD students who spend 5-6 years of their lives learning both, so the atmospheric science and then some statistics, or statistics and some atmospheric science, and really contribute to sort of to new methodology in answering questions that we might not have been able to answer before. I don't know if that was that gave you enough of an answer to that question. Okay.
So I'm going to move on to one of our next questions.
Sure.
One of our members of our audience is super interested, sitting on the edge of their seat, to hear the results of the ice sheet sea level rise. Kind of what results have come out of that, and what are the predictions about the distributions of sea level rise or ice sheet melting that you have seen in your work?
Yeah. That's a perfectly sensible question when I set up the talk by saying the statistics in the future, right? And I focus mostly on the process, partly because I wanted to talk about what the role that statistics played in this. Because so anyway, I hope you understand the role of the process. Now there's quite a lot of debate among different groups on the precise values or distributions that you get, but even within across all of those different methods that are used in different data sets, there's still some very strong, consistent pieces of it. So, for example, I think, so Klaus, you can correct me if I'm wrong on this, the Ipcc put together for the end of the century sea level rise projections about 0.3 to 0.5 meters ballpark, right, was sort of the most probable. And then it gets, that's just the most probable, that's the spike in the middle. And then also potentially values all the way up to about a meter and beyond. And then we also have some scientists who are studying things like Dave Pollard, who have very particular physics that they're concerned about. So MICHI, and I'm trying to remember what MICHI stands for, the
marine ice sheet instability.
Marine ice sheet instability, right? MICHI, M-I-C-I, marine ice sheet instability, sorry, marine ice shelf. Anyway, I forget the exact one, but MICHI. So these are things that are unstable in the ice sheets that might actually potentially raise those levels to being even much higher than what the Ipcc said. But even with sort of the most conservative things, there's clearly expected to be a significant amount of sea level rise by the end of the century, and possibly much more.
Okay. So I've got a related question,
Sure.
kind of related to how the process of doing this ice sheet research, kind of more on the data collection front. So you mentioned the satellite imaging. What other sources are being pulled together? Is the data collection quality actually good? And then how do you choose the parameters that need to be considered when there probably are maybe more than you can model?
Wow, that's a very sophisticated question. How do you choose the parameters that are modeled? That is a really great and really difficult question to answer. Something that our group has spent some time on. So the dials, I showed a few dials, there's tons of dials on these, for these models. What ends up happening is that there are lots of dials, but typically for the things that you care about, a small subset of them are the ones that really have a big impact. The other things might have some impact, but their impacts are small. So we can usually whittle down by some combination of the experimentation, which is playing around with those models, and also scientific knowledge. You can whittle it down to a relatively small number, but even the small number tends to be big enough to give us pose challenges. So something that has worked on is trying to increase the number of parameters that we can consider, which turns out to be an extremely difficult problem, both statistically and computationally. So for instance, a recent thing that we did was we expanded what the number of these parameters that we were taking into account to about 11 for a recent model, whereas previously it was about 3 to 4 to 5. And as we increased it, we do see some changes in the uncertainties. That's a really good and very challenging question. That's one of the many things that we have to worry about when modeling such a complicated system. What was the
data collection?
Oh, data collection.
Data sources. How good is the data quality?
Okay.
That kind of thing.
So that's a question that is the details of which are best directed to Dave Pollard, our collaborator. But sort of at a high level, much of we have many different data sources. So some of it is the satellite images, which tend to be pretty high quality. But then there's also data that we use to sort of approximate how the ice sheet was behaving, potentially hundreds and thousands of years ago, which are using these ice core data and many other sources. And there's a lot of modeling that goes into producing those data. So those data, you could give a separate talk about how to produce those kinds of data from the past. And they're sort of, again, there's a lot of approximations that are used. And some of those, we have to then, when we put the pieces together to estimation, we will try our best to adjust for the fact that there are parts of the data that seem a lot more noisy than other parts. And sometimes, for some of the things that are measured, you might actually know exactly the device that's being used, how error-prone it is, and then we will incorporate that into our modeling. So we really, a big interest is incorporating that kind of noise into our results. But yeah, those are really great questions.
So another question that is kind of high level, maybe even slightly philosophical about statistics. I think you'd be a good person to tackle this question. It says the discipline of statistics has had an uneasy relationship with the concept of causation. And in prediction of ice sheet change or climate, determining causation is critical to fixing the problem. So how do you account for causation in the modeling that you do?
Oh, very, very interesting question. That is a deep question. In fact, one of our faculty here in our department is an expert in causation and is teaching a course on that all semester. So let's talk about causation in this context. To some extent, of course, it's a natural system, so we don't have the best and cleanest way to study causation, of course, is to run an experiment, and we can't go back 1,000 years and toss in more CO2 in the atmosphere and then see what happens and toss less CO2 and compare that. That would be the nicest thing to do. We can't do that. So what do we do with the information that we have? Well, a lot of the most interesting things that you can do, there's a whole area called detection and attribution within climate science and stats. But my quick answer to this would be a lot of these computer models, these physical models, give you some way of understanding things that are causation-like, not precise. You are never going to be able to answer those things exactly, but you can get a pretty good sense of it. And here's a bird's eye view of it. You take the physics of the process, and then you say, I'm going to run these models for over an extended period of time, and then I'm going to put in no carbon emissions, and then I'm going to do exactly the same thing, hold all of that constant, and here's a computer experiment where I put in carbon emissions, and a lot of it, and then I see what happens in these two scenarios, and then I compare that with what has actually happened. And so that gives you a way to understand, within the realm of these physical models, whether this kind of emissions actually, if what we're observing is compatible with not with sort of what would have happened with the climate on its own, versus if the only way to really explain this is if you put in those emissions. So that's one of the ways in which people try to answer this old question of is what we're seeing due to human activity. So you can get at things that are causation-like, but of course to answer those things extremely rigorously is very difficult. That's a really great question.
Okay, so this next question is also kind of a tricky question about statistics and how humans and society perceive statistics. Because this question says, statisticians, they strive to discover the most likely outcome. Statistics are, conveyed in a distribution. But when they're communicated sometimes to the public, either a piece is taken or they give it one value. It might not be communicated in complete, in its entirety. And so, do you have any tips for how the public can really, understand the whole truth of what to believe when it's statistically based knowledge that's being communicated?
Oh, that's a fun question. So one thing I often ask is the number of people who tell me, "Oh, you're in statistics. Isn't it true that you can prove whatever you like using statistics?" Or and this might be the first time that I'm meeting this person, so it's an interesting topic to kick off the conversation. Isn't it true that using your profession you can lie? Is what they're saying, right? And my answer to that is, since I have some experience with this, my answer to that is, you're absolutely right. But I can also lie using English. Right? I don't need statistics to lie. I can, you can give things that are dishonest a sheen of plausibility by obfuscating, hiding things, showing stuff selectively. Of course, it's very easy to be dishonest, but I don't think it's limited to statistics. But it so happens that because statistics is so important to actually evaluating evidence, if it's so important, then you can abuse it. So it's very powerful. It's also rife with opportunities for abuse. So let me come to the second part of that question, which is an interesting one. So if you're a regular person looking at talks, and maybe you haven't had the opportunity to study some particular problem in depth, which actually even statisticians, we don't, if we're given some information from another field, unless we go and spend an enormous amount of time, we don't necessarily figure out every last thing in there. But you develop really good instincts. It's sort of, I'd say my analogy would be to when you have an uncle forwarding you a strange article that talks about something that sounds plausible, but is sounds conspiracy theory-ish. Your radar goes up, and you think, oh, wait a minute, there's no such university called Johns Hopkins University, right? It's Johns Hopkins. So when you read an article that sort of pretends to be, it gives this sheen of being real science, but it's not, you can quickly pick up on it. Some things are much more subtle. If it's super technical, you don't have the expertise to figure it out. Then I think what you need to do is maybe look up a few different scientists in the area. Maybe the best way for me to summarize my response to this is, trust experts over people who are just weighing in on blogs, right? So, and I can give lots of examples. I'm not saying that experts are infallible. That's not what I'm saying. But if you are trying to gather evidence for something, and if you're trying to decide whether you want to believe something or not, an offhand comment by somebody who's a blogger is maybe not something that you want to take as seriously as maybe an interview with someone who knows this very well. I'll give you a very quick example. One of my colleagues did an interview recently with a newspaper, and I forget the details of this, but he said some very sensible, very reasonable things about probability and maybe in a couple of different areas. And then I happened to find some blog posts that were had somebody who had read the article and was saying that he was deeply skeptical of what this professor had said, and then said some things that were completely nonsensical, but he said it with great confidence. And so, if your cousin sends you a blog post like that, don't pay attention to it, as maybe you go back to the original source and see what kind of information there is there. People weigh in too much with a great deal of confidence on things. So my summary of that is try to go listen to the experts, and then if you take some an introductory stats class, you would learn something like this, where you think, ask the question, what was the sample size of this? Maybe there's some information about that in the article. What was the sample size of this? Was it something that seemed scientifically done? You can start building instincts, but at some level, you're going to have to trust some source that you read. So there's no foolproof way of figuring out what's correct and what's not.
Okay, thank you. We had a few, so I'm trying to combine some related questions here. We did have some questions about kind of the translation between the science that's done in these interdisciplinary teams and then the policy making at the end of it. And so how is that translation? Has that translation process started to happen with the work you're doing with ice sheets, and who in the policy world might it be being received by? And just kind of that process of going from research to maybe actionable decisions that are being made.
Okay, so I'm really glad that my collaborator, who's an expert in decision making and actually talks more to stakeholders than me, is here. Maybe he'll have something wise to say. So my work, so I've only been in this area for about 8 years or so. So it's only because it takes a while. And I have not myself worked on anything that's related to policy, statistician, and I've been working on statistical methods to help solve these problems. The policy-oriented things, I don't know that I have myself anything directly to point to from the work that I've been doing, but I don't know if Klaus, if there's anything that you want to point to. Sorry to put you on the spot. You were kind enough to come here this morning, and here I am harassing you.
No free lunch.
Yeah.
Well, there are a few avenues how this works. For one,
Oh. Sorry.
so many scientists work at agencies or for reports for decision makers. So there's the Ipcc, the Intergovernmental Panel on Climate Change, which is designed to communicate science to decision makers. And many of those things that are published are then taken up by that. Otherwise, yesterday I emailed with a person from the Army Corps of Engineers. There are institutions in the US which use scientific information that are based on peer-reviewed science. And then there are institutions at Penn State which are funded by federal agencies where they're outreach specialists, which are paid by NOAA, for example, by federal funds, our taxpayer money, to go and engage with decision makers at the coast on how to actually think about building and coastal defense. So, we wrote a paper on what's the potential water height in Norfolk, Virginia, for obvious reasons, because people build seawalls there. That's one of the cases. So there are many avenues to go. Some are very formal, like peer-reviewed governmental reports where governments actually vote on the language, and some are less formal, but also federally funded by outreach extension specialists. This is really, really hard, but it's something which I think increasingly we need to train the new generation of scientists and engineers to actually be halfway decent at this.
Thank you so much. And apologies for bothering you.
Well, thank you so much for your guest answer to that question. And just just a reminder, if you have questions that come up while he's answering a different question, the floor is still open for you to raise up your index card and for someone to come grab it from you for it to be asked. I have a question here about how, in a collaborative team with lots of different scientists involved, when you publish or when you share your results with the world, is it easy to, how do you credit your contributions to the team and the over results or outcomes? Is it very easy to kind of distribute the credit across all the fields that are involved, or does it typically kind of sit under one discipline or another, and then everything's kind of seen as supporting in the background? Yeah,
that's something that can be quite challenging. But why my collaboration here is so fantastic is we've, I think, figured out exactly how to make this work very well. So we always have both our groups have postdocs and graduate students, and what we always have to look out for, there's the education aspect as well as the research output aspect. What we always look out for are, of course, the junior members of our team the most. And any work that we do that is this collaboration between stats and climate and risk analysis involves some piece that's a little bit more heavily statistical, and then it involves some piece that's a little bit more heavily risk analysis or climate science oriented. And so what we do is we will find the piece that's heavily statistical, and then the stats grad student and I will take the lead on that, and then write things that are a little bit more statistically technical in that paper and send it to statistical outlets. And then the stuff that's more climate science oriented, Klaus and his postdocs and grad students will take the lead on that work, and it will be sent to the scientific domain journals. And so we have these parallel threads heavily overlapping. And then sometimes a method will be developed here and then used to do an analysis in a different situation. And so we always have a parallel thread of papers that go to different communities, because what we don't want is to do all this work and have it only land up in one community and not the other, which defeats the purpose. We want to have an impact on science. We want to have an impact on statistical methodology. And we've managed to figure out how to do that quite smoothly. But it takes a while, and it's not always the easiest. I hope that I answered the question fully. Okay.
Okay, so we have time for 2 more questions. The first one should be a quick and easy one about the ice sheet research. They were curious about, comparing any projections you might have for ice sheets 20 years from now to what they look like today. If you have any information about where we are today, where they might be 20 years from now, based off your work.
So let me just think. So all the plots that I can think of are sort of 2100 are the ones that are coming to mind. So I don't have a quick answer to the 20 years from now.
Is there a place you might suggest they go to look for that information, maybe? Or?
Yeah. So actually, if you Google IPCC sea level rise projection and put down a date, it'll give you an idea. So some of the stuff that we did, again, this is our group and our research, which some of the stuff that we did for about 2100 was around a little over a meter in sea level rise at the end of the century, was sort of the most likely, and then but many higher levels were also plausible, and lower levels were plausible but less so. So I don't know, that gives you a hint at it. 2100, as a friend of mine was just reminding me the other day, so kids who are born now, 2100 is not as far away as we used to think. Kids who are born now are likely going to be around 2100. So this is not some distant future. It's not our great-grandkids or something. It's kids born now, or who have already been born recently. Anyway.
All right, thank you. And this last question is a broader question, kind of about interdisciplinary research at Penn State. Do you think more could be done at Penn State to combine different disciplines in a way that could advance scientific research?
Well, so let me take this as an opportunity to say how impressed I am by how Penn State's doing things. And this is this is genuinely how I feel about how this is working out in many ways at Penn State, is we have all these institutes that if they're interesting hires who are sort of at the boundary between two disciplines, they will support the hires, and they will not, sometimes you support somebody financially, then you require a huge number of things out of them, but they support them and then let them be scientists, which is really, ultimately, you want academics to be able to work on things that they find most enriching. And so Penn State's been really, I've been very impressed, also as department head, because I work with institute directors quite a bit, this willingness to consider people who are sort of on the edge of, who are interested in working across disciplines and just supporting them. So Penn State is doing very well. We could always do more. Sometimes really limitations can be because of certain disciplines not being so willing to allow for people who are unusual, who are dabbling in other things. So certain disciplines and sometimes certain departments are very conservative, and they view good research as falling into this particular thread, in a particular thread that doesn't allow for people to work across disciplines. And so for junior researchers, that's really, especially if you're a new faculty member, that makes it really hard for you to be interdisciplinary. And it just makes it hard in general. But overall, Penn State's doing pretty well. We can continue. I'm sure we could keep doing more of this. But it's a pretty exciting place to be an interdisciplinary scientist. And it's, at least from my perspective, it's been great.